So good morning to all of you. So let's begin our sessions. As you can see from the title, we are going to talk about solid state devices. Okay, how to understand solid state devices in an easy manner. That is what we want to do. At any point of time, if you have a question, please raise your hands and ask a question, right? Do not feel hesitation in interrupting me. I will also be asking you, giving you some time for questions occasionally, but you need not wait for that time. And let's see how this all proceeds. So in the beginning, let us see what are the expectations out of this session. So at the end of this 6-hour session, you should be able to state why study of solid state devices. Why study solid state devices? You should be able to sketch the current voltage characteristics of a PN junction, bipolar junction transistor and a metal oxide semiconductor field effect transistor, that is a MOSFET. You should be able to describe the evolution of solid state devices, namely diodes and transistors. You should be able to state the steps involved in analyzing a solid state device to obtain an equation for its current voltage characteristics. You should be able to state how mobile charges are generated and transported in semiconductors. You should be able to distinguish between a BJT and a MOSFET. You should be able to explain the rectifying operation of a PN junction and amplifying operation of a transistor, which could be bipolar or MOS, without using equations or energy band diagrams. That is just using reasoning. Explain the features and utility of energy band diagram of a semiconductor. Write and explain the equations based on diffusion carrier transport that are commonly employed to model a solid state device. State some standard approximations employed to simplify the solution of the above equations. And finally, state how to check and remember a device model equation and what precautions should be taken while making calculations with it. Now let's look at examples of some devices. Small signal devices. Small signal devices are those which carry small amounts of current. Now you will ask me, what is meant by small amounts of current? So currents of the order of say microamperes to tens of milliamperes. That would be a device, right, which is a small signal device. There are two types of devices shown here. One is diode, which has two terminals. A diode is used for rectification. It is also used as a light emitting device, LED. There are other applications of diode also, we have not shown here. And then you have a 3-terminal device called the transistor. As we will see, you can have two different types of transistors, MOSFET or BJT. In fact, there are many different types of transistors, but in this course, in these 6 sessions, we will focus on just 2 of these, that is BJT and the MOSFET. Now let's see what are other types of devices. Power devices. So as against small signal devices, power devices are those devices which carry large amounts of power. So maybe even hundreds of amperes. Devices which can carry that high a current. You can see the construction of the device is a little different from the small signal case. One thing that is evident is that power devices are bigger than small signal devices, that is evident. What you also find is that the power devices have some sort of an arrangement to fit them, to enable us to fit them to a heat sink which can remove a lot of heat that is generated in the device. Now what is the heat generated in a device? You know that it is given by the current through the device multiplied by the voltage across the device, IV. that gives you the amount of heat generated per unit time, power dissipated. So that power, unless you dissipate it, the device temperature will go up and it may malfunction. So you need an arrangement to fit this device to a heat sink. So that is why you find here that there is a strip and a hole. Through this hole you can insert a screw and screw this device and fit it to a big heat sink that can remove heat. Similar arrangement is there for other devices also. You can see that. Microwave devices. These are devices used at very high frequencies. Now as engineering students, all of you should know what are the range of frequencies which can be called as microwave. So please take this down as a question. What is the range of frequencies that is called as microwave? Right? Take this down and find out if you do not know. So you can see the construction of microwave devices is a little different. The sizes are small, and the package, the way they are held, right, encapsulated, is different. What is the particular property of the encapsulation? The property is such that the encapsulation is such that parasitic inductance and resistance capacitances will be very small in this device. Why? Because at very high frequencies, even small amount of inductance or capacitance can spoil the device operation. So we don't want any extraneous capacitance or inductance. Only the capacitance or inductance that is offered by the device should be there. Nothing else should be there. Bottom of the table gives you the symbol that is used. So two-terminal device, that is diode, is represented using this kind of a symbol, two-terminal diode. So here, based on the arrow, you can figure out which direction is the forward current and which direction is the reverse current. So in this case, for example, left hand side is anode and this strip is the cathode. So when you have left hand side positive and right hand side negative, you say it is forward biased. As against this symbol for transistors, this is a bipolar junction transistor. It has three terminals. Many of you might already know the top terminal is called the collector, the middle one is the base, and the bottom is the emitter. The MOSFET is inherently a four-terminal device. You can see this. So like the BJT, it has three terminals, namely the top terminal, that is called the drain, which is analogous to the collector. Middle one is the gate, analogous to the base, and the bottom one is the source, analogous to the emitter. So drain and collector, they mean more or less the same thing. Emitter and source, they mean more or less the same thing. Something that sources or emits carriers, that is source. Something that collects or drains away the carriers is called collector or drain. And the controlling terminal is the base in the bipolar transistor and the gate in the MOSFET. Now there are two types of MOSFET shown here. We will come to that later, but let us talk about the fourth terminal here. The fourth terminal is the bulk or the substrate. We will discuss more about these four terminals later when we discuss the device operation. So as against bipolar transistor, you have two different types of MOSFETs, namely what is called an enhancement type or normally off and normally on device. So we will discuss these types also later when we discuss the device operation. Now let us talk about why study solid state devices. Solid state devices enhance performance, reliability and cost effectiveness of energy systems and information systems. All the various systems that you come across in electrical engineering can be broadly divided into two types: information systems and energy systems. Let us see what are these. So energy systems are those which generate, distribute and regulate as large energy as possible. On the other hand, information systems are those which store, process and communicate information expending as small an energy as possible. So while in energy systems you want to manage large amounts of power, in information systems you want to manage large amount of information expending as small an energy as possible. That is the difference. So the construction of the two systems and the type of devices used in the two systems will be different. Now what happens is these systems historically have been built using different types of devices. For example, vacuum tubes, right? So if you take more than 70-80 years ago, the devices were made of vacuum tube before 1950s, right? Now what we are saying is, if you replace those other devices like vacuum tubes by solid state devices. So what do you mean by solid state device? A solid state device is a device made out of solid where the current flow happens in a solid. As against this, in a vacuum tube, the current flow is happening in vacuum. Okay? So here is an example of a vacuum tube diode. So it has two terminals. This is anode and this is cathode. This is a heating element which heats this plate so that it can emit electrons. So when this diode is conducting, there will be flow of electrons from cathode to anode. So cathode is emitting electrons and they are reaching the anode. So the conventional current would be from anode to cathode, but you know that electron flow is opposite to the conventional current flow. So you can see here the conduction of electrons is happening in vacuum, right? This is like a incandescent lamp bulb. So inside you will have vacuum. Why do you need vacuum inside? Because these heating elements, the plate and so on, they will be heated, and at that high temperature, if they are exposed to air, then there will be a reaction and the material will get oxidized and it will get spoiled, it will not function. That is why they had to be arranged in a vacuum tube. So this is a vacuum tube. I suggest tonight after the class all of you go and do an internet search on vacuum tube diode, vacuum tube triode, and see the construction of this device and how it works. So here we will not discuss the vacuum tube much. I only want to point out that the conduction happens in vacuum in this device. In a solid state device, on the other hand, let me draw a solid state diode. All of you perhaps know this P-N junction. So this is P, this is N, and you have a terminal here, this is the anode, and a terminal here which is the cathode. So this is a solid state diode. Because here the electron flow is from N to P, but it is in a solid, for example silicon, right? So this electron flows in solid, whereas this is in vacuum. That is why there is a solid state diode, whereas this is a vacuum tube diode. Like that you can have a vacuum tube triode, right? And the corresponding solid state triode is called a transistor. So if you replace systems which are made from devices based on vacuum tube with systems which are using solid state devices like this, then the performance, reliability and cost effectiveness will be very high. Okay? To give you some examples, you are able to send satellites out which can work for many years only because you are using solid state devices there which can work for many years. So reliability is very high, they don't fail very often. Vacuum tube fails very often, used to fail often, right? For example, nowadays you will know that people are replacing incandescent lamp bulbs by LEDs. Why? Because the amount of current that is consumed by an LED for giving a particular amount of light is much less. The LED works for many more, much longer time than incandescent bulb, right? So that is the reason why systems which are made from solid state devices are more reliable. they are very cost effective, the cost is less, their size is smaller, and they can do many functions. Your cell phone is possible only because of the solid state device. Palm top computers only possible because of solid state device. See the kind of things that they can do. Now that is the reason why it is important for us to know how these devices function. Now some examples are shown on the slide here. On the left hand side you see a mechanical calculator used many tens of years ago, whereas this is an electronic calculator. The mechanical calculator could only do additions, multiplications, subtractions, etc. Whereas you know the electronic calculator can do many things, right? All of you are aware of what all it can do. Another example is shown here, microsensor clusters. You can see here on the left hand side a wrist-worn environmental monitor. Now this is something like a watch worn on hand, and it has so many things. It has an acceleration sensor, humidity sensor, temperature sensor, pressure sensor, etc. And this is an example of a smart pen for signature verification. So it has acceleration, force and tilt sensors. Okay, so having discussed why we should study solid state devices, because they are all around us, anywhere you look around and you will find solid state devices. So let us see what are the current voltage characteristics of this device. Let's start with a diode, which is very simple. You apply a DC voltage V and you get a current I through the device. Now what is the shape of the current voltage characteristics? This is how it looks like. As engineers, we should pay particular attention to the magnitudes of quantities, orders of magnitudes of quantities that are used here, right? So the voltage axis is in volts and the current axis is in milliamperes here, because we are discussing a small signal device. Further, another important thing you find here is that the positive current axis, which gives forward bias currents, is in milliampere scale, whereas the negative vertical axis, which gives the reverse current, is in nanoampere scale. So the two scales are not the same. Often what happens is students remember the shape of the curve, but they do not remember the orders of magnitudes of quantities. Okay, as we will see, the same curve will appear of a different shape if you change the scales. Now before we come to that, let us see other features of this curve. So beyond some reverse current, beyond some reverse voltage, you have breakdown in which range the current increases rapidly, even if you increase the voltage by a small amount. In the forward direction, this voltage here, beyond which the current is rising, is called the cut-in voltage, and all of you know for silicon devices it is about 0.6 to 0.7 volts. Now let us look at the same curve on some other scales. This is how the curve looks like if my negative y-axis is also made in milliampere scale. So then you do not really see the reverse current at all, because reverse current is of the order of nanoamperes, as you can see from the first graph. So if I choose the axis to be in milliampere scale, I cannot show nanoamperes. So the reverse current will coincide with the zero of the vertical axis almost. Let us look at it on another scale. Supposing I choose nanoampere as the scale, vertical as well as horizontal, then how will the curve look like? Now I am able to show the reverse current as in the first case, but in the forward direction you can see that the voltage is really very small if you see on nanoampere scale. Also in both milliampere scale and nanoampere scale, the curve appears to be, the slope of the curve appears to be continuous here at the origin. Here also the slope is continuous, whereas here when you change the vertical scale on the positive side as compared to the vertical scale on the negative side, you see that there is a change in the slope. Now this is very important. Many students do not pay attention to these details. So what we are saying is, if this is milliampere and this is nanoampere, this axis is always volts, then your curve will be like this and here it will be like this. So you have a discontinuity in slope. If I make this also milliamperes, then the curve will not go like this, it will simply go like this, because this nanoampere cannot be seen. If I make both vertical and horizontal as nanoamperes, then I will see this curve and here this curve will go up like this, because when current is nanoampere, voltage is very small. Okay, so students should pay particular attention to this. Let's look at the current voltage characteristics of a BJT. This is a little bit more complicated. BJT is a 3-terminal device. So you see, you have several possibilities. So you have 3 types of characteristics called common emitter, common base, and common collector, right? Now E is emitter, B is base, and C is collector. Now why do you have these 3 types of characteristics, something that was not there in a diode? In the case of diode, you had only one type of characteristic. Because it's a 3-terminal device, I can choose any of the 3 terminals as a common terminal and apply voltage to the other 2 terminals with respect to the common terminal. And since any of the 3 terminals can be common, you have 3 different situations. We will sketch the characteristics for common emitter, which is commonly used. Common emitter, that means I will apply the voltages or currents with respect to emitter. So here you can see the emitter is common. I am applying a voltage between collector and emitter as I did for a diode, but between emitter and base I am now applying a current, and this current controls the current between emitter and collector. So base is the controlling terminal. Now let us see how the collector current changes when you change the collector emitter voltage for any given base current. This is the shape. So we are plotting the collector current versus the collector emitter voltage for different values of base current. So each curve shows you the variation for a constant base current. Now please note that we have put a modulus for VCE because the collector to emitter voltage you can see here is negative. Collector is negative with respect to emitter. And since we prefer to put all the characteristics in the first quadrant, we want the current axis to be positive, voltage axis to be positive. So that is why we have used modulus for collector current as well as collector to emitter voltage. You know the nomenclature that in electrical engineering, if a current is flowing out of a terminal, then it is negative, and a current flowing into the terminal is positive. So any system in electrical engineering, if it has a terminal, if the current is flowing into this terminal, it will be regarded as positive, and if the current is flowing out of the terminal, that current will be regarded as negative. That is the convention. Similarly, you can see here, this current flows out of the base terminal. That is why we have put a modulus here. Now once again, as in the case of the diode, for the transistor also we should pay attention to the magnitudes of quantities. You can see here, it is a small signal bipolar transistor. The current is of the order of tens to few hundreds of microamperes. The voltage is in the order of volts, and the base current is of the order of microamperes. So while the collector current is of the order of tens to hundreds of microamperes, the base current is of the order of microamperes, and the voltage axis is of the order of volts. Now you can also have what are called input characteristics. So this is called output characteristics. The input characteristics would be the input current versus the input voltage. So the collector terminal is referred to as the output terminal here, and the base is the input. Okay, that is why this is called output characteristics. Collector current characteristics are called output characteristics, whereas base current characteristics are called input characteristics. So IB is of the order of microamperes here, as you can see here, this is of the order of microamperes, and base to emitter voltage, that is the voltage between this P plus and N terminals. So as a function of VB, how does it look? So it is like a diode, right? It is like a diode like characteristics, the cut-in voltage being close to 0.6. So first, before we start explaining any characteristics, we should first know what are we trying to explain. So that is what we are plotting here. We are going to explain these characteristics later. Right now we are only showing what is the type of characteristics we get. You can see here that if I keep the base current constant, that is if I keep this current constant and change the collector to emitter voltage, then collector current varies as shown here. It increases rapidly, and after a few hundred millivolts, less than a volt, it saturates to a constant value. If you increase the base current, you get the same shape, but the current now saturates to a higher value, and so on. The point of saturation here is slightly increasing, but always remains about 1 volt or less. Now let's come to a slightly more complicated situation, that is the MOSFET. A MOSFET is a 4-terminal device. Now you can imagine there will be so many possible characteristics in this case, but we will show the characteristics for the most common biasing arrangement, and that is called common source. So like common emitter, you have common source characteristics. Now here, this is the source terminal, this is the drain terminal. Drain is analogous to the collector and source is analogous to the emitter, and this is the gate controlling terminal, which is analogous to the base of the bipolar transistor, and this is the substrate. So that is how you have 4 terminals. So you are applying a controlling voltage instead of a controlling current in a bipolar transistor. We had said that we must appreciate the difference between a MOSFET and a BJT. That is one of the goals of our session. So you can see that while a MOSFET is a voltage control device, a bipolar transistor, as we had shown now, is a current control device, but we can show that it can be regarded as voltage controlled also, but a MOSFET is always only a voltage control device. The reason is you have an oxide layer or insulator here which does not allow any current between the controlling terminal, that is the gate, and the substrate. So no current is possible through the control terminal. Now you can also have a voltage applied across base, across the bulk and the substrate, that is a VBS, but the source should always be reverse biased with respect to bulk. So in this case we are considering an N-channel transistor. So you can see that N-channel transistor means a transistor in which the current is controlled by electrons. So in this case the N side should be positive with respect to the P side because it should be reverse biased. Now what are the characteristics that we get for this situation? So this is ID, drain current, as a function of drain to source voltage. So this current here as a function of drain to source voltage. In bipolar transistor we plotted collector current as a function of collector to emitter voltage. Now unlike the bipolar transistor, you don't have any modulus here for VDS and ID, because you can see that the current ID is into the device. In this case this is a NPN transistor where the current flow is because of electrons. Let me take you back to the bipolar transistor slide, and you can see there that this was a PNP transistor. You can have a PNP or NPN transistor, right? So here it was a PNP transistor. That is why the collector current was outward. If you take an NPN transistor, the collector current would be inward. Okay, come back to this transistor. This is NPN. This is a N-channel MOSFET. So here the drain current is into the collector, into the drain terminal, and you have the drain to source voltage. When you vary this voltage, how does this current change? So you can see that you keep your VGS constant and vary VDS. As in a bipolar transistor, here also current increases and then saturates, and as you increase your gate to source voltage, your current increases. However, some differences can be seen here from the bipolar transistor. Let's go back to the bipolar transistor. Here, when the base current increased in equal increments, 1 to 2, 2 to 3, 3 to 4, the collector current appears to increase also in equal increments. Okay, so the increment in collector current in response to increment in the base current is equal, whereas in a MOSFET you can see there is a difference. So for equal increments in voltage, for higher voltages you get more increment in the drain current, right? So that is a difference. Another difference is also that the saturation voltage, that is the voltage at which current saturates, is a little higher than in the case of bipolar transistors. Now since MOSFET is a 4-terminal device, whenever we sketch a family of curves, this is called a family of curves because you have a number of curves here, not just one curve. So when you sketch a family of curves, you can show 3 quantities, ID, VDS and VGS, whereas this is a 4-terminal device. So I must tell what is the condition of the 4th terminal. So that is why you need to write here what is the VBS. Now this particular set of curves are drawn for VBS equal to 0. This means source and bulk have been shorted. In the case of BJT, you do not need any such information because it is a 3-terminal device. A BJT is a 3-terminal device. Now MOSFET does not have input characteristics, unlike the BJT, because the gate current IG, that is the current through this terminal, is 0 because of the presence of the insulator here. Let's briefly see some stories, how these devices evolve, right? Little bit of history. In 1874, a person by name Braun, B-R-A-U-N, discovered that he could make a rectifier with a simple arrangement like this. So there was a semiconductor material and he just brought in contact a metal wire. That is why it is called a point contact diode. So this is a semiconductor S and this is a metal wire. And to his surprise, he found that this was showing rectifying characteristics, right? Diode like characteristics. In 1874, which was the device that was used for rectification? It was vacuum tube. That was commonly used, right? And this was a great discovery. You can see that I have put a D there in brackets, which tells whether it was a discovery or an invention. You know the difference between discovery and invention. Discovery is something that you stumble upon accidentally, right? Without a plan. You are looking for something and accidentally you discover, you get something else. That is a discovery. But invention is something that you conceive in your mind, you have a plan and then you try to realize it, right? And then it is realized, then it is invention. So this was a discovery, and accidentally while doing experiments, Braun discovered that this gives you rectifying characteristics when you connect a power supply. So this was the first solid state device, solid state diode, 1874. Metal semiconductor contact, that is how it was. Later in 1925 and 1934, two inventors, now you can see these are inventors, Lilienfeld and O'Heal, they proposed an idea. They said that if you can make a diode, a rectifying element from solid state like this instead of a vacuum tube, why can't you make a vacuum tube triode which is used for amplification? That is a 3-terminal vacuum tube device. Why can't you make it in a solid? So they proposed an idea. So they said, our idea is the following. I will take a semiconductor block and then I will take a metal electrode. So this is metal and this is semiconductor. Now if I apply a voltage between these two, it will behave like a parallel plate capacitor, metal and semiconductor. So for example, for this polarity, electrons will be attracted here and here you will have positive charges. Now without these electrons, the semiconductor doesn't have much resistivity. That is why it is called a semiconductor. It is not like a conductor, right? So with these electrons, the resistivity will change a lot. It will become more conducting. Then they said, I will use these electrons to pass a current by connecting another cell like this, so that I will get a current. So electrons will move like this from negative to positive. Now this flow of electrons can be controlled by this electric field which is between the positive charges of the metal and negative charges. So this was their idea, to control this current here which you are getting, this is I, using this voltage, that is the controlling voltage. So this is somewhat like a MOSFET. This is the gate, this is the insulator in between, and this is the semiconductor. This is the gate source voltage, and here you have drain and source terminals. So this is supplying electrons here, so this can be called as a source and this can be called as a drain. So this was the idea. They didn't realize it. They said that why not we make a structure like this. They filed what is called a patent. So this was the idea on which people started working. Let us start realizing this in practice. So it would work as an amplifier. As people were working, in 1940, OHL discovered a PN junction. Note that this was a metal semiconductor junction. Braun discovered metal semiconductor junction. The PN junction was discovered in 1940, which is made only from a semiconductor. Metal semiconductor junction is a contact between metal and semiconductor, whereas PN junction, the P and N regions are made in a semiconductor material. In 1948, people discovered the bipolar junction transistor. You see, everybody was trying to make this device, which is called a field effect transistor. So in fact, when this device was proposed, nobody called it a transistor, right? It was a field effect structure. In fact, people called it vacuum tube, the people called it solid state triode. That was the original name. But because of the way it functions, people called it, they said it is a field effect device. What is field effect? Control of a current in the horizontal direction by a vertical field, electric field. That is field effect. So in terms of the construction, it has 3 terminals, 1, 2 and 3. That is why it is called a triode. Okay, and because it involves current through solid, it is called a solid state triode. But from the point of view of the operation of the device, the phenomenon that is giving rise to the device operation, from that point of view, it is called a field effect device. Okay, so trying to realize a field effect device, these 3 scientists, Shockley, Bardeen and Brattain, here, they discovered the bipolar transistor. It was an accidental discovery, right? You are trying to realize a solid state triode of this type, but they discovered a solid state triode of another type. Bipolar junction transistor is also a triode, right? Because 3 terminals. Okay, so what is the construction of bipolar transistor? You know that. It was something like this. So this was the base semiconductor. And these were the 2 contacts they had made. So in fact, the name given to this was point contact transistor. Now I am using the word transistor. This word was proposed by these 3 scientists, Shockley, Bardeen and Brattain, for this 3-terminal device. Now what is the meaning of the term transistor? Let us see. Let me write here first. Transistor. So they said when they connected the sources here and tried to measure the currents. So the current between 2 terminals was affecting the current between another 2 terminals when this point was very close to this point. That was the arrangement. So they said what is happening is the current is being transferred from a low resistance circuit to a high resistance circuit. Okay, that is what they found. Now when we discuss the operation of the PNP transistor or NPN transistor, bipolar transistor, we will see why it is low resistance to high resistance. But right now I want to explain only the term, how it has arisen, transistor. So low resistance to high resistance. So they said it is like a transfer resistor. Current is being transferred from a low resistance to high resistance. So transfer resistor. And they removed this FER and RES and join these two terminals, join these two remaining parts of the words, it becomes transistor. That is how it became a transistor. Yes, so I am getting a question, let us see what the question is. In BJT input characteristics, if the collector emitter voltage increases, the potential barrier of the base collector also increases, or simply collector emitter voltage is directly proportional to the potential barrier of the collector base junction. So how it is possible to collector current increase? Yes, now this question we will reserve until we discuss the operation. Right now I have told you I have not discussed the operation of the bipolar transistor. I only discussed the characteristics. We are going to explain how you get those characteristics, right, shortly in the next coming sessions. At that time we will try to answer this question. Okay, so I explained to you how the word transistor has come. Transfer resistor, you remove FER and RES and join, you get transistor. Okay, that's how the 3-terminal device or the triode, solid state triode, was given the name transistor. Okay, so this is a device working on a different principle than this device which was conceived, right? This is a field effect device, whereas this is a junction effect device. Okay, so we will explain the operation later. I am only telling you first the difference in names. So bipolar junction transistor, its principle of operation is very different from the field effect, but the field effect device and bipolar junction transistor both can have 3 terminals. That is a common thing. So both can be used for amplification. Now after the discovery of the bipolar junction transistor, people stopped working on this device, trying to realize this device. You can see from about 1930 to 1950, 20 years people have been trying to make this device and were not successful. Okay, and they accidentally discovered this device, but this was good for amplification. So they said, okay, let's use this. Why bother? We started with this, but we have got something that works for us. So in 1952, Shockley invented what is called the junction field effect transistor, a variation of this. You can do a net search and find out how a junction field effect transistor works. In 1958 came the idea of integrated circuit. The people who proposed this idea, one of them has got a Nobel Prize in physics. This is the only instance of a person who is from an engineering background was given a Nobel Prize in physics. Okay, why? Because it is the idea of integrated circuits that he came up with, which was responsible for putting lot of devices on a single substrate and miniaturization of the device. And this miniaturization of the device gave rise to new physics, because when you try to make devices in very small scale, lot of interesting phenomena happen, there is a lot of new physics in it. And so it was felt that this invention of the integrated circuit has propelled a lot of activity in physics, and that is why this person was given Nobel Prize in physics. What is the name of this person who is an engineer who invented the integrated circuit and who was given Nobel Prize in physics, and which year did he get it? Right? Please do a net search today. Okay, take down this question, find out who it was. Now after the invention of the integrated circuit, it was realized that this particular device, the field effect device, was more appropriate for integrated circuit, for putting many devices on the same substrate, same semiconductor substrate. That is why it is called integrated circuit. Bipolar transistor was good as an individual device, but if someone wanted to put many such transistors and diodes on the same substrate, they found that this device is more suitable for that kind of a thing. Therefore, people again diverted their attention to this device, the field effect device, and in 1960, within a short time after 1958, within a couple of years, they could come up with a practical device that is called the metal oxide field effect transistor. This was possible because lot of developments had taken place in semiconductor technology by then. Okay, so this is very interesting. The idea of semiconductor triode proposed in 1930s was realized only in 1960 in practice. There are many other devices which were proposed after that. I am just showing you one device, that is a metal semiconductor field effect transistor. As I have mentioned in the beginning of this as our session, there are many different types of field effect transistors. You can do a net search, find out how many different types of field effect transistors are there. Bipolar transistor, there are not many varieties, okay? Bipolar transistor, not many varieties. But field effect transistors, lot of varieties. You do a net search, find out what are the different types of bipolar transistors and what are the different types of field effect transistors, okay? This is the third question. So I have given you 3 questions for finding answers from the net, right? Different types of FETs and different types of BJTs, bipolar transistors. Question number 3. Question number 2 was, when did the person who invented integrated circuit get a Nobel Prize, and who was that person? And another question which was in the beginning, can someone tell me what was that? For net search, I gave you one question for internet search tonight. Anyone? I want to see whether people are attentive. Tyagaraja College of Engineering. What was the first question for which you are asked to do net search?
Operation of vacuum tubes.
Operation of vacuum tubes.
Can you hear me?
Good. I think that makes it 4. So I asked you 4 questions actually, which was another question. Right in the beginning of the session I asked. The one more question on net search.
The range of microwave frequencies.
Correct. Very good. The range of microwave frequencies. What frequency range is called microwave? Okay. Very good. I am happy that you are all attentive. Okay. So let's proceed further. How do you analyze a solid state device for its IV equation? So we are only giving the procedure. Please note, first we are giving some facts, right? And we are going to explain in detail the operation and so on, right? Now the first step for analyzing a solid state device is to partition the device into space, charge and neutral regions. Any device, you take a PN junction, a bipolar transistor, a field effect transistor, any device you want to analyze its operation. What are the steps in which you should go about? That is what we are discussing, a general approach. You must partition the device into space, charge and neutral regions. Now, I want to know how many of you students know the meaning of the word analysis. What does the word analysis mean? Any student who can answer the question? What does the word analysis mean? We often use the term analysis. Okay. Let me tell you what does the word analysis mean. One thing all of us should do is, whenever we come across a term and we do not know its meaning properly, we must always make an effort to understand the meanings of each of these terms. Today, because we have internet at our disposal, in fact, we can get answers to all our questions very easily. Okay? So please make this as a habit. As engineers or as scientists, one of the things that we must learn is to get the precise meaning of every word that we use. No word we should remember or know its meaning vaguely. We must know precise meaning. Okay? So let me tell you, what does the word analysis mean? Analysis means separation of a whole into parts. Anything we want to analyze, we must separate first into parts. Then understanding the parts in isolation. Then combining the understanding of the different parts so that we understand the whole. Let's put it down. What does analysis mean? Separation of a whole. WHOLE, whole, means any anything that you want to analyze. The whole is the complete, okay, any object that you want to analyze. Separation of a whole into parts. We can show it like this. So suppose this is the whole, separate it into parts. Then that is step 1. Step 2, understand the parts in isolation. So you are breaking down a complex problem to smaller problems, right? This breaking down is involved in analysis. Understand the operation of the parts. In isolation. In isolation. What does it mean? When I want to understand, let us say this part, I don't bother about the other parts. That's the thing. Actually, different parts may be influencing each other. For example, I cannot understand my body as follows. Can you understand a human being? You remove the hands, you remove the head, right? The human being would be dead, right? So we use this kind of things for most cases inanimate things. Even for living things, we can use analysis in some different way, right? So when we try to understand the parts, we don't bother about the other parts. So therefore, there is some intelligence involved here. I must separate the whole into parts in such a way that the parts should not influence each other. So there is some intelligence involved here. What kind of separation you can do so that you can understand them in isolation without bothering about others. Okay, the third step is combining the understanding. Of the parts to understand the whole. Right? So we understand each of these parts separately, then we combine and try to understand the whole. That is the meaning of analysis. So an ability to do this for anything that we come across, right, will be called an analytical ability. So when you say scientists have or engineers have good analytical ability, what does it mean? It means whenever they are presented with something, they understand using these steps. They separate a complex situation into parts and they are intelligent enough to separate in such a way that one part will not affect the other very much. Then they understand parts and then they combine the understanding, right, so that they get understanding of the whole. Same thing we are applying to current voltage characteristics, right, of a solid state device. So step 1, partition the device into space charge and neutral regions. Look at the slides. Step 2, analyze each region separately to obtain the distributions of the carriers and potential. So when we say understand a part of a device, what exactly we mean? This is a general definition for, so what we have written on the board is a general definition for analyzing anything. Okay. Now in the context of semiconductor devices, what does the word understand the operation mean? So specifically, understanding the operation in semiconductor devices means getting to know the distributions of carriers, that is electron and holes, and the potential. These three quantities. I should know what is the variation of the electron concentration in the device as a function of distance, as a function of time. I should know what is the variation of the hole concentration in the device as a function of distance, as a function of time. I should know potential, how it varies in the device as a function of distance and time. Okay. Now let me give you an example of this. Suppose I take a simple resistor. Okay, simple resistor, and I apply a voltage. So there is a semiconductor block which has uniform conditions inside. This is voltage, this is current. Now if I plot N, P and psi as a function of x, How will it look? Suppose this is an N-type semiconductor, right? I am assuming that you know little bit about N-type. We are going to discuss. If you do not know, well, you will appreciate a little bit of what I am saying, and that is sufficient. So it is N-type semiconductor, so electrons are in a high concentration. So since it is uniform, the N-type concentration of electrons will be the same. A high and constant concentration of electrons with distance. Whole concentration on the same scale, it will be much less as a function of distance. Potential, how is it varying? You see, left hand side is positive, right hand side is negative. So your potential is varying linearly because it is a uniform semiconductor. Your potential varies linearly from one value to another value. If I assume the potential on the right hand side here to be 0, then the potential here is equal to V, right? That is the voltage V. So here it is V and here it is 0. So this value is 0 and this value is V. So this is psi variation. Now this is the picture we have for a uniform block of semiconductor to which a voltage has been applied, and I want to find out the current. I have to use this information to get the current. Okay, so electron concentration, hole concentration, potential as a function of distance. If I know this, then I say that I have understood this semiconductor device. Okay, you can plot it as a function of time also. In this case, since I am applying a DC voltage, all conditions are constant with time. So at any t, this will be the picture at any time. Now if I change this DC voltage to some alternating voltage or transient voltage which changes with time, then the conditions may also change with time. Okay, so that is what is meant by understanding. So step number 2, analyze each region separately to obtain distributions of carriers, NP and potentials. Before I move to step 3, let me give an example of step 1, partition the device into space charge and neutral regions. So here, in fact, this whole region is neutral, charge neutral. Whereas if you take a p-n junction, and those of you who know how a p-n junction works, you know that a region near the junction will be charged. So this is the space charge region. And these two are neutral regions. So what we are saying is, you want to understand a p-n junction, you separately and try to understand the space charge and these two neutral regions. Then you try to combine the understanding. Bipolar junction transistor. Suppose it is a PNP transistor. You want to understand this, here you have space charge region, you have another space charge region here, and you have these neutral regions, right? So you must understand these neutral regions and space charge regions separately, then you combine, then you will get to know how the bipolar junction transistor operates, right? And for each of these regions, space charge and neutral regions, I should know N, P and potential as a function of distance and time. That is the meaning of understanding the parts. Okay, step 3, combine the information regarding N, P and psi obtained in different regions, ensuring continuity of these parameters across the boundaries separating the regions to obtain the complete picture regarding the terminal current as function of the voltage applied between device terminals. So here I have understood space charge region separately, neutral region separately. I must combine the information. When I am combining, I should take care that the electron concentration should be continuous across the boundaries. The whole concentration should be continuous across the boundaries. Potential should also be continuous. So using this continuity, we combine the information mathematically, right? Then we get understanding of the complete device. So this is the approach we are going to take to understand any device. So now begins our explanation. So this will be in detail. So far we have told many facts, right? Now we are going to build up explanations in detail. So I want to understand any semiconductor device. The first step, I should understand how mobile carriers can be generated in semiconductors, right? Because you know we are going to talk about current. Now current flow is because of charges which can move. So if I want to get the current in any device, I should know what is the concentration of mobile charges, and I should know what velocity with which they move. If I combine the concentration and velocity, I get current. You know that formula for the current density, right? The formula for current density is J is equal to the charges which are moving, their charge, the concentration of these charges, and the velocity, Q and V, that gives you current density J. An engineer or a scientist should always confirm a formula like this which we write using dimensions. So Q is Coulomb, N is concentration per centimeter cube, and V is velocity of the carriers. So that is centimeter per second. So you see your unit for J is Coulomb per second is amperes, and this is centimeter square. So J is ampere per centimeter square. Okay. So this is the formula, basic formula for current. If I want to know the current in any situation, I should know the concentration of carriers, I should know the charge on the carrier, that is Q, and I should know the velocity with which they move. If I know this, then I can find out what is the current. Therefore, to begin with, I must know how N carriers are created, mobile charges are created in semiconductors. Okay, let's begin with that. Then we'll move on to complicated situations like a p-n junction and a bipolar transistor. First, let us take a simple uniform semiconductor. Let's understand that. Here is the atomic arrangement of a semiconductor, namely silicon. Please pay particular attention to this arrangement. So what is shown here is a unit cube, the basic arrangement that is repeated in the crystal. So you repeat this cube in 3 dimensions, then you get the actual silicon, piece of silicon. Now the dimension of this cube is 5.43 angstroms. It's very easy to remember, 543, right? And there is one decimal there. So 5.43, okay. Now what happens is students always remember the numbers but they forget the units, whereas units are more important many times than the numbers. Angstrom unit, angstrom, 1 angstrom is how many centimeters? I want an answer from someone. 1 angstrom is how many centimeters? Any student can answer this question. Yes. Okay, someone has given the answer. Which college? St. Thomas College of Engineering has given an answer. It is 10 power minus 8 centimeters. 10 power minus 8 centimeters. See, this is a very important point. All engineers and scientists should note. So we should have a feel for various dimensions, actual intuitive feel for various dimensions. For example, when someone tells you that my house is 2 kilometers from your house, you have a feeling for 2 kilometers means how much. If I were to walk, how long it will take. If I were to take a scooter, how long it will take. So all these ideas you have about 2 kilometers, right? Now like that, we should have some idea about all the dimensions that we use. Let us look at this dimension, 1 angstrom, right? So one thing you come to know now is when you are talking about atoms, sizes of atoms and so on, then you will not express the size in kilometers, right? You will express the size in angstroms. Just as if I want to say what is the distance between Chennai and Madurai, I will not express this distance in angstroms. I will express the distance in kilometers or hundreds of kilometers. I will not use centimeters also, right? So like that, in different situations you use different dimensions, units, because only when you use those units it gives you a feel about the particular parameter, physical parameter, right? So now you know the angstrom is the unit used for atoms. Let me give you a better physical feel for angstrom. Let's take the dimension micron, 1 micron. This is 10 power minus 4 centimeters. or 10 power minus 6 meters. Micron is micrometer. Micrometer. Micro means 10 power minus 6. 10 power minus 6 meters. Now, how much is a micron? If you want to get a feel for this, can someone tell me, give me an answer, give me some idea. Like I told you about, let us say, the length of my finger. If I ask you what is the length of my finger, you will express it in centimeters, right? And you will say maybe it is 6 centimeters or maybe 8 centimeters for some. And if it is a baby, right, it could be even 2 or 3 centimeters. But you will express the length of the finger in centimeters, right? So it gives you a feel. Tell me, give me a feel for a micron. Tell me something whose thickness is of the order of microns, something that you can feel. Any student, BATU? No, that is also saying 10 power minus 8, that is the centimeters. Hair thickness, very good. Somebody says hair thickness. Which college is it? BATU, that is, okay, can you please tell me BATU, where are you from? Lonere, okay, Lonere, you are from Maharashtra, that is very good. So we are having people from all over the country. Fine. So hair thickness, that's good. Okay, example, somebody has asked me example of energy and information system. I will come to that later, let me complete this part. So our hair is 30 to 40 micron thick. Our hair thickness is 30 to 40 micron, 30 to 40. So 1 micron is 1/30th or 1/40th of the thickness of the hair. Now 1 angstrom. Please do this exercise. 1 angstrom is how many microns? 1 angstrom is how many microns? Okay, please do it. You can do this exercise after my session. That will give you a feel for an angstrom, because now you know hair is 30 to 40 microns. If you know how much is 1 angstrom, it will tell you how small is an atom. Okay, let's get back to our slide. I will answer your question on energy and information systems later. So here a silicon unit cube size is 5.43 angstrom. So you can see in this cube you have atoms at center at the corners of the cube. So 8 corners, then 6 face centers. The blue atoms here are at 6 face centers. So the cube has 6 faces, and then you have 4 atoms inside, 2 near the bottom diagonal corners and 2 near the top diagonal corners, which is perpendicular to the bottom diagonal. So it is something like this. I am only showing the inside atoms here on the board. Other atoms can be clearly understood. So inside atoms will be, say this is A, this is B. So one is near this corner and another is near this corner, and other 2 are near C and D. And what is the distance? So it is, supposing I say this dimension is A, this atom is A by 4 along this axis, A by 4 along this axis, A by 4 along this, like this, right? So A by 4, A by 4, A by 4, that is what it is. Similarly, you have other atoms located there. That is the arrangement for silicon. Further bonds have been shown. You know that each silicon atom is bonded to 4 nearest neighbors. Okay, that is the kind of bonding. So you can see that here each red atom which is inside the cube is bonded to 4 neighbors. They are 1 corner, that is this one, and 3 face centers, these 3 blue atoms. So bottom face, the vertical face close to you, and this side face, the centers of these 3 faces. Okay, that is how you have 4 atoms bonded to 1 atom. Similar arrangement is there for others. And if you repeat this in 3 dimensions, then you can show that each of these corner atoms also you will find them bonded to 4 neighbors. Now since it is difficult to work with this 3-dimensional arrangement, what we do is we work with a 2-dimensional picture, something that is very easy to visualize. So you can see here each silicon atom is bonded to 4 neighbors. Okay, and many times we do not even draw this circles and so on. we simply show the arrangement as like this. It is understood that at each point of intersection you have a silicon atom. So this is a representation of the silicon crystal, right, bond representation of the silicon crystal. So this is a two-dimensional representation of 3D crystal. We will be always using this whenever we want to explain various properties of semiconductors, semiconductor silicon, properties of silicon, like how charges are created and so on. We will be using this two-dimensional arrangement instead of the three-dimensional picture. Now let us see how mobile carriers are generated in semiconductors. Let me take a look at the questions actually. What are the questions? Because if they are related to something that I am going to discuss now, I will do that. Otherwise, I will do them later. Yeah, so let me look at those questions. What happens if voltage VBS in MOSFET is neglected? Okay, this we will answer when we take up the MOSFET operation. Then example for energy system and information system. I will do this towards the end of this session. Then BJT characteristics, this I will discuss when I discuss the operation of BJT. Okay, then let me see. Difference of transmission through vacuum and through air as a medium. Yes, that is what we are going to discuss. So this question will be answered in coming session. How carriers move in the two different cases. Okay, so fine. So three of these questions about bipolar transistor, MOSFET, and how carriers move in vacuum and in this thing will get answered in coming sessions. The question on example of energy system and information system. See, for example, a computer. Computer is by and large an information system, right? Because what are you doing there? You are using the computer for mathematical operations, calculations. You are using the computer for emailing, transmitting information. So processing and transmission of information, communication of information, storage of information. So you store all your files, information about various things, about papers and so on, and in the computer. So you can see that computer is a unit which is storing, processing and communicating information. So it is an information system. You would like to do all these operations with minimal energy loss, right? So if you have, for example, a laptop, you would like to use it on battery for as long a time as possible. So consumption of energy should be small. So this is an example of an information system. What about energy system? Okay, switched mode power supply, which you use to power your computer when the electricity goes off. That is a energy system, because there you want a power supply which will supply energy for as long a time as possible. So you want to manage large amount of energy, right? So switch mode power supply that is used, or stabilizer, voltage stabilizer that is used with your refrigeration or computer is an example of a energy system. Okay. So if things are not clear, you can ask me further questions later on. Let's move with the present discussion on creation of charges in semiconductors, mobile charges. So let's look at the slide. Now what is the picture of intrinsic silicon at 0K? What is the meaning of the word intrinsic? So you can assume that the word intrinsic means almost pure, right, which has no defects and so on. At 0 Kelvin, the picture is as shown here, right? So this is the two-dimensional arrangement of atoms, right, that we have drawn on the board. The same thing is shown here. Intrinsic silicon at 0K, there are no mobile charges or carriers. You can see here that all silicon atoms are bonded to 4 nearest neighbors. That is what this matrix here shows, horizontal and vertical lines. Each point of intersection is a silicon atom. Now suppose I raise the temperature more than 0 Kelvin, what is going to happen? Here is an animation. Okay, this is a three-dimensional picture. At t equal to 0k, it shows atoms in some crystal, right? At t equal to 0k, all the atoms are still. Now, at t greater than 0k, what happens? So, this is the picture, right? Each atom is vibrating about its position. You can see the atoms moving there about their position. So, this is what happens if you raise the temperature. The extent of vibration will increase, right? The atoms will vibrate at much higher frequency and amplitude if you raise the temperature. Okay. So, what is the result of this? Let us see. So, when you want to see the result, we will come back to the two-dimensional representation. So, you can see here what is happening at 300K, for example, room temperature. You can see that some bonds are broken. You can see some circles here. It means that particular bond is broken. Okay. So, here for example, if this bond is broken, I show a circle, a vacancy. Why? Because an electron from there has left the bond. Okay. Now, that is what is shown here. So, you can see here 5 bonds have been broken, okay, in this slide, and it has resulted in a free electron. So, when a bond breaks, an electron is becoming free. Why is the bond breaking? It is because of the vibrations, atomic vibrations. So, when a atom is vibrating vigorously, an electron that is attached to the atom becomes free, right? It is somewhat like this. Suppose imagine something is stuck to my body, right here, and then I start moving vigorously, right? So, what is happening is that thing which is stuck to me just dislodges from my body. That is how a bound electron becomes free. Now, you will ask me, all the atoms are vibrating. Why are only some bonds breaking, right? Shouldn't all the bonds break? No, because this picture is random. The picture of the vibrations is random. You would have seen the atoms are vibrating in all possible directions. Different atoms are vibrating in random direction, right? They are not coordinated. Now, you know that whenever picture is random, you have a distribution of various things like energies and so on. Suppose you take the population of students in your class, all of them will not have the same height. A very few will be very tall and a very few will be very short, and most of them, others will be average height. The same thing happens in a crystal for t greater than 0k. All atoms are vibrating, but if very few atoms are vibrating with high energy, their frequency and amplitude is very high, vigorously vibrating, and because of that, only these few atoms which are vibrating very vigorously, they will release their electrons to become free. How much energy is required to break a silicon-silicon bond? It is 1.1 electron volt. Is the bond energy of silicon. So, if the vibrational energy of the silicon atom anywhere becomes more than 1.1, then an electron which is participating in the bond right next to the atom can become free, and only a few atoms in the crystal will have more energy than 1.1 electron volt. So, that is what is shown here. Carriers contributed by silicon ionization or thermal generation, which yields an electron hole pairs. Now, so what is happening is you have an electron and you also have a vacancy. That vacancy is referred to as hole. So, every time a silicon bond breaks, you get a pair. One is free electron, that is called the electron, and a vacancy, that is called a hole. We will shortly see why the vacancy is also given importance as a mobile charge. Now, the process of breaking of a bond is called ionization. So, silicon ionization. It is also referred to as thermal generation. Thermal generation. Why? Because it is happening due to atomic vibrations, and which is because of raised temperature of the crystal. So, because of temperature, this thing is happening, silicon atoms are getting ionized. Now, two processes are happening simultaneously in an isolated piece of silicon. Along with generation, there is also what is called recombination. Now, why should there be recombination along with generation? If there was no recombination, there was only generation, then the concentration of electrons will go on increasing with time and concentration of holes will go on increasing with time. Electron hole pairs concentration will go on increasing with time. Why? Because there is generation. So constantly bonds are breaking and electrons and holes are getting created. So evidently this process will go on and the silicon will blow up, which is contrary to our experience, because we are maintaining the silicon at room temperature. Silicon is not melting. We are maintaining the silicon at room temperature. If that is so, and if generation is happening, we are also, so we know that the silicon is not blowing up, it is being maintained at room temperature, but we also know that some silicon atoms bonds are breaking. But so how can the silicon not blow up and bonds keep breaking? So evidently some bonds which are broken are getting re-established, right? So that process is called recombination, when a free electron jumps into a vacancy. So that is what is shown here. So the arrow in which from a solid dot, which is an electron, and a arrow getting into the vacancy or a hole is a recombination process. So you can see that for every electron hole pair generation, there is an electron hole pair recombination happening somewhere else. So this is exactly like if you take a human population, there is birth and there is death. You cannot have only birth. If you had only birth, the population will go on increasing and it will explode. But it doesn't work that way. We know that. We have deaths also. Now if birth rate and death rate are equal, then we will have a steady population of people. Now sometimes students get this doubt. If birth rate is equal to death rate, if number of people born is equal to number of people dying, then there should be no population. But we see a population. Why? The important point is, after a person is born, he doesn't die immediately, right? So someone else is dying. The person lives for some time. So in other words, every person has a lifetime, right? That is why you have a steady population. If the lifetime of people were 0, then you will have no population. A person is born and immediately he dies, he or she dies, right? Then you will not have any population. So because people have lifetime, they stay for some 50 years, 60 years or whatever. Therefore you have a constant population if birth rate is equal to death rate. Same thing applies in the case of electrons and holes. So electron hole pairs are generated, then they stay for some time. There is a lifetime associated with these, and thereafter they recombine. Okay, but at any instant, whenever a birth is happening, whenever a generation is happening, some recombination is taking place. Some other electron and holes are recombining, right? So that a steady population of electrons and holes is maintained. So electron hole pair generation rate is equal to electron hole pair recombination rate. That is what we see here, resulting in a steady carrier concentration. So let us look at this slide once more. So first I am flipping the slide back. We showed only generation, right? A bond breaking resulting in electron hole pair. Now we added recombination at equal rate. So this is the complete picture, generation and recombination, okay, happening at the same time. But please remember, whatever is generated doesn't recombine immediately. Some other thing recombines at the same instant, and always generation rate will be equal to recombination rate. Only then you can have a steady population concentration. So that is what is written here. The rate being equal, you get Ni equal to Pi. N is electron concentration, P is so-called vacancy concentration, positive charge concentration, and I refers to intrinsic semiconductor. Now let us look at this positive charge a little bit, or the vacancy. Why the vacancy acts like a mobile carrier or mobile charge of positive polarity. It is easy for us to appreciate how the free electrons will contribute to current. When you apply an electric field, the free electrons can move, right? But how do the vacancies move? So the hole or the vacancy is like a bubble in a liquid. So this is the analogy, the bubble analogy of a hole. So you see, if I take a tube and I fill it up with liquid except for a small space, that is a bubble. Now if I tilt this tube like this, what will happen? You will see the bubble moving up. Actually what is happening is the liquid is moving down. Why is the liquid moving down? Because this is air, and when you tilt it, the liquid will try to get into this air because this is like a vacancy. Because of gravity, the liquid has to move, right, to a vacant region. So liquid is trying to move. In the process, the bubble is moving up. So actually it is liquid moving, but you are seeing it as a bubble moving. Why? Because the liquid is a lot of volume. A bubble is small, so you can concentrate on the bubble, focus on the bubble. So movement of the bubble actually reflects the movement of the liquid. Liquid is moving downward when you tilt the tube like this, but the bubble is moving upward. Okay, so direction of the movement of the liquid and the bubble is opposite. So just as the movement of the liquid is captured in the movement of the bubble in this tube, similarly the movement of the bonded electrons, in silicon via the vacancies, it's captured in the movement of the vacancy. Let us see how can the vacancy or a hole move. So suppose this is our picture of silicon. Somewhere there is a break, that is the vacancy. It has given an electron. That electron can move about randomly, right, free. Now what happens to this vacancy? What can happen is an electron from this bond, for example, can get into this vacancy, so that this bond will be filled up and the vacancy would have moved here. Then it can happen that an electron from here can get in, right, and the vacancy will move here and this bond will be established. That is how the vacancy has sequentially moved like this via the various atoms, right. The same as the liquid getting into the bubble. Similarly, a bonded electron can slip into the vacancy. Energy is not required for this purpose, right. For an electron to slip into the vacancy, you don't need energy. For an electron to become free, you need 1.1 electron volts. Okay, but for an electron to slip into a vacancy, you don't need any energy. It is somewhat like a student shifting from his or her own seat to a nearby seat which is vacant. You don't need much energy for it. It is lateral shift. But if you want to go out or run around, then you have to become free, right? Then you need more energy. So the vacancies can also contribute to movement of electrons. So when you apply an electric field to a semiconductor, then you will have movement of free electrons, and in addition you will have movement of bonded electrons or bound electrons. How can bound electrons move? They move via the vacancies left behind by the free electrons, just as the liquid moves through the bubble, okay, in the same way. So if you now try to measure the current in a semiconductor, if you only try to calculate the current in terms of the free electron current, your current will be in error. You will not be able to get the full current, because in addition to the free electrons, there is a current because of bound electrons through the vacancies. When temperature is 0 Kelvin, there are no vacancies, there are no free electrons, therefore no current, because a bonded electron or bound electrons can move only if there is a vacancy. Suppose this tube was full of liquid. If you tilt the tube, will the liquid move? No, the liquid won't move, right, because the tube is full of liquid. So in a similar way, at t equal to 0 K, since all the bonds are intact, there can be no movement of electrons. But when t is greater than 0 K, some free electrons are created which leave behind vacancies, and through the vacancies the bonded electrons can move, giving rise to current. That is why the vacancy is called a hole. Just as the bubble moves in the opposite direction to the liquid, the vacancy moves in opposite direction to the movement of bound electrons. Therefore, it is given a positive charge. If you apply an electric field, electrons will move in some direction, whereas the vacancy will move in the opposite direction. Therefore, the charge of the vacancy is opposite to that of electrons, it is positive. That is how the hole is given a positive charge. It is a positive mobile charge. Now, we have looked at the intrinsic semiconductor so far. Now let us look at extrinsic semiconductor. Okay, that is phosphorus doped silicon. We have introduced impurity, phosphorus. How will the semiconductor now behave? Phosphorus doped silicon. As against intrinsic semiconductor, if you add impurities to it or if there are defects, it is called an extrinsic semiconductor. Extrinsic semiconductor. Okay, intrinsic means it is almost pure. Extrinsic means it contains defects or impurities, opposite of intrinsic. Now, let us see what is going to happen if you add phosphorus. So here is the picture. If you add phosphorus atoms, then phosphorus is a group 5 element, silicon is a group 4 element. So that means phosphorus has 5 electrons in the outermost orbit. 4 of these electrons will participate in bonding with the neighboring silicon atoms. That is what is shown here. But the 5th electron, now what happens to the 5th electron? That is the question. Okay. So what happens is that the 5th electron will still revolve around the phosphorus atom when temperature is 0 Kelvin. Okay. When temperature is 0 Kelvin, it will revolve around the phosphorus atom. That is what is shown here. It will be bonded to the phosphorus atom. But the bond energy between the electron and phosphorus atom will be small as compared to the bond energy between them when the phosphorus atom is outside. Why? Let us look at this point. What is the bond energy of this electron to the phosphorus atom here? So let us look at a hydrogen-like model, right? Let us look at a hydrogen-like model. Radius of the orbit in a hydrogen model. You have a nucleus at the center and electron revolving around it. You can calculate the radius. I will give it as an exercise to you. You can see the internet. What is the Bohr radius of hydrogen model? R. Bohr radius of hydrogen. Okay. It will be in angstroms. Again, you are coming to atomic dimensions. When you try to calculate the Bohr radius of hydrogen atom of this electron, then you will use the dielectric constant of the medium between the electron and the nucleus, and that dielectric constant will be epsilon naught. That is the permittivity of free space. But when you put the phosphorus atom in silicon, which is the picture here, the dielectric constant of the surrounding or environment of the phosphorus atom, it changes to silicon. And now in silicon, so Bohr radius of hydrogen atom in silicon, if you put in silicon, then this dielectric constant will change to epsilon naught epsilon r. Dielectric constant of silicon should be used because lot of silicon atoms are there. And what is dielectric constant of silicon? This is 12. So the permittivity of silicon is 12 times the permittivity of free space, which is epsilon naught. Now if you take the formula for Bohr radius, which I have given you as an assignment, look into the internet, formula for Bohr radius, you would have done it in your chemistry. You will find that the energy associated with this is inversely proportional to energy of the electron is inversely proportional to epsilon r square. From the radius you can find out the energy, epsilon r square. So suppose you take the phosphorus atom in vacuum, you will get some energy. Moment you put the phosphorus atom in silicon, the energy will reduce by epsilon r square factor, dielectric constant. Okay. Now epsilon r is 12, epsilon r square will be 144. So the bonding energy between the electron and the nucleus in vacuum is 144 times more than in silicon, or the bonding energy in silicon is 144 times less because of dielectric constant than in vacuum, right? So that is why the bond energy between this electron and this phosphorus atom is very, very small. Silicon to silicon bond energy 1.1 electron volt. Phosphorus atom to the fifth electron bonding energy 0.045 electron volt. Okay, 0.045 electron volt. What is the ionization energy of silicon? It is 1.1 electron volt. So you see the bond is very weak. The bond of this electron to the phosphorus atom, okay, here is very, very weak as compared to bond of the one silicon to other silicon. And therefore, when you raise the temperature, okay, at 300 K, all the impurities will become ionized. So you can see that the circle is gone. Circle was representing a bond, but now the electron has become free. Therefore, the circle has vanished. Look at this. T equal to 0 K, there was a circle showing that there is a bond between the electron and nucleus. Whereas T greater than 0 K, at 300 K, the bond has vanished. So each of the electron has become free from the phosphorus atom. Okay. Now in addition, some silicon-silicon bonds will also break. So in addition to impurity ionization which yields carriers of one polarity only. So you can see that here. Okay, we'll continue with this later. Let me look at questions. Why carbon is not used as a semiconductor material even if it is included in fourth group? A good question. Carbon is also a semiconductor, but its insulating property is much more than silicon. Band gap, energy gap of carbon is very high. So you know, people are considering the use of carbon in the form of diamond. Nowadays people are talking about diamond as a possible semiconductor material, right? Nowadays people are talking about it. Okay, so that is the answer to the question why carbon is not used. Nowadays people are trying to use it in different forms, right? For example, people are trying to use graphene, diamond, graphene and all that. Next question. Is there any relation in bond energy and concentration of electrons? No, it depends on what bond energy are you talking about. If you are talking about silicon to silicon bond energy, it doesn't depend on the electron concentration. Basic difference between JFET and a MOSFET. Both are field effect transistors. In one case, the transverse controlling field. Let me show with a diagram. Suppose I want to talk about current flow in p-type region. So set as this is a MOSFET and this is JFET. Okay, I want to talk about an n-channel JFET and n-channel MOSFET. So JFET, n-channel JFET will look like this. This is the n region in which current is flowing between say drain and source, and the gate will be made of junction, PN junction. So this is a gate. Imagine that both these are connected together. Okay, So that is why it is called a junction FET. So now you will have a space charge region here. When you vary the voltage of this gate with respect to source, the space charge region will vary and the amount of current that can flow between drain and source will change. In a MOSFET, the current flow will be as follows. That same N region will be like an inversion layer here. So this will be the N region, this is P, and this inversion region will be created by a gate electrode which is away from the semiconductor. So there is an insulator here or oxide. That is why the word oxide in MOSFET. There is an oxide layer, insulator separating the gate controlling terminal from the semiconductor. Here there is no insulator separating the controlling terminal from the semiconductor. Okay, so here junction is controlling directly. Here metal oxide semiconductor, that is controlling the current. That is why it is called MOSFET. So the current will be, now here you connect drain and source. So this is drain and this is source. Current flow will be right next to the insulator here. Okay. So you can see the two differences. One difference is the controlling element is a metal oxide semiconductor unit that is controlling the current in this direction, whereas here the junction is controlling the current in this direction. Second is the current is flowing in the junction FET in the bulk of the silicon, whereas here this is the silicon below the insulator. So the current is flowing right at the interface of silicon and silicon dioxide. So in a MOSFET the current flow is at the interface, whereas in a junction FET it is in the bulk. So those are the two differences between junction FET and MOSFET. What is the function of fourth terminal in a MOSFET? So fourth terminal in a MOSFET is substrate. We will know more about it when we discuss the MOSFET operation. Why the direction of hole flow is considered as the direction of current flow? Look, it is like this. Suppose this is a semiconductor, you are applying a voltage. Now, the electrons in the semiconductor will always move from negative to positive terminal. All electrons will move like this. Now, when you are asked which is the direction of current flow in the terminal, you will say current flows into the positive terminal, right? Positive terminal of the battery gives you the current and current flows in, right? But if you see the electron flow, it is from negative to positive. So conventional current flow, that is a flow of positive charge. You always think in terms of positive charge. So direction of the current is same as direction of positive charge. Now the electrons move in the opposite direction to the direction of positive charge. Hole is a positive charge and therefore direction of current is the same as direction of hole current, hole flow, right? So that is why the current is in the direction of hole flow. Why the direction of hole flow is considered as direction of current flow, not considering direction of electron flow? No. So we are considering the electron flow, but the electrons always move in the, so as you can see here, when there is a drift, you consider the direction of electron flow also into account. When we come to diffusion, you will see both electrons and holes can move in the same direction, right? But then their contributions will cancel out, okay? Because you can see that if this is a negative charge, positive charge, both are moving in the same direction, you can club them together, and negative and positive together is how much? Zero charge, right? So therefore, if electrons and holes are together moving in the same direction, it amounts to no current because together the charge is zero. Okay, so all the students, thank you very much for listening to me. I hope things have been interesting and we are going to answer all your questions will get answered as we develop our idea of how current flow, right? How current flows in semiconductors, junctions, transistors and so on. We are going to discuss this in detail in the later sections. We will close for the day.